The next topic we want to take a look at here is planes. How we want to be thinking about planes is we want to think of them as these two-dimensional flat surfaces in R3 that extend in every direction to infinity. Similar to lines in R3, we're going to have several forms of this equation. The first should look rather familiar to us, the vector form. The vector form equation has the same components or similar components to the line equation for R3. In order to define a plane uniquely in R3, we need any point on the plane, and two direction vectors on the surface. This is because we have a two-dimensional surface now, a plane, as opposed to a one-dimensional surface, a line. The next form of the equation that we're going to take a look at will be the scalar form. This should look rather similar to the standard form equation for lines that we learned in grade 9. It's not a coincidence, however. Both of these act very similarly because they're both one dimension smaller than the dimension of the space they're in. For example, the scalar form of the plane represents a surface that's two dimensions in R3, whereas the standard form equation for the line represents a one-dimensional surface in R2. The reason that these behave so similarly is that the coefficients attached to the variables, which we may or may not have realized when we learned this in grade 9, is that these actually correspond to the normal to this surface. So for example, if we had the two-dimensional example of a line, A and B would be the normal to that line, or the direction that would be perpendicular to it. Similarly, this is true for the plane. The coefficients A, B, and C represent the normal vector to this surface. And as we know, the normal vector will be perpendicular to any vectors on that surface. So let's take a look at how we can come up with these equations for a plane. If instead of being given two vectors, we're instead given 3 points. 3 points, as long as they're distinct, can always define a unique plane. From these 3 points, we can determine the two direction vectors that we need to satisfy our vector form equation. To begin, we'll do the same thing that we did with this type of problem for lines. We'll determine one of the direction vectors by subtracting two of the given points. Next, we'll create another direction vector on that surface by subtracting the other 2 points. We now have obtained two distinct direction vectors that are on this surface, and we can now select any point that we know on the plane. In this case, we know 3. Substituting into the vector form equation that I stated above, I chose to use point C and the direction vectors I determined, and we end up with this equation for the plane. Well, how can we go from this vector form equation to the scalar form equation that we mentioned before? We said before that in order to write the equation in this form, we need to know the normal. So the normal must be perpendicular to all vectors on that surface. Well, fortunately, we actually know two vectors that are on this surface, and we also learned a mechanism for finding vectors that are perpendicular back in the second chapter for vectors. That was the cross product. So if we take the direction vector 1 and direction vector 2 and plug it into our cross product formula, we'll actually obtain a vector that's perpendicular to both, and will actually be perpendicular to all vectors on that surface. Now, if we take our scalar form equation like we started with and substitute in the normal, we can obtain this form of the equation. We're missing one piece of information, however. We're missing this constant d. Well, how can we determine it? This equation must be true for all points on the plane. So if we were to know some points on the plane, we could plug one in and solve for d. We actually happen to know 3 points on the plane, and in this case, I selected point A because it's the origin, which eliminates all 3 other variables, leaving just d, and we determined that d is equal to 0. With this last piece of information and the normal we calculated above, we can substitute into the scalar form equation that I stated before, and we end up with the solution here. Next, let's take a look at intersections of planes. Before we get into a specific solution of how we go about it, let's talk about the different types of solutions we can expect. First, we could expect that it's a possibility for 2 planes to be identical and on top of each other. How would we identify this? This tends to be the easiest type of solution to identify, as both equations will be scalar multiples of each other. So for instance, in this example, if it was possible for me to take the equation for plane 1 and multiply it by some non-zero constant to make it equal to the second plane, then these two would be coincident. The next type of solution that we could find would be that they would be parallel and distinct. So that means that they have the same direction and they're separated. They move in the same way. If this is the case, then we'll identify this by looking at just the normal vectors. If the normal vectors are scalar multiples of each other, but the constants don't line up, then it must be the case that these are two distinct planes with the same directions. The final case that we can have for intersections is that if they actually do intersect and are not in the same plane. The only way this can happen is with these two-dimensional surfaces, they'll intersect in a line. This will be our typical case. So given these two distinct planes, checking quickly that these normals are not scalar multiples of each other, we'll move on to the next step. So our first step in solving this type of problem will be to choose a variable, it won't matter which one, and eliminate it. In this case, I chose to eliminate x. In order to do that, I took this equation 2 and subtracted it from equation 1, ending with this equation. The next step in our solution process will be to pick one of the remaining variables, and we'll call it our parameter. In this case, z equals t. This will yield our first of the three parametric equations. Next, let's substitute z into the previous equations. So I now know that z is equal to t. So this will be my second parametric equation. Y is equal to minus 3 over 4 plus t. Well, now that I know what z is in terms of my parameter and y is in terms of my parameter, I'm going to sub it back into my equation 1 and end up with an expression that has only x's and t's. Simplifying this expression, I end up with a solution that in this case doesn't involve t, but that won't always be the case, but this will in fact be our third parametric equation. We can then express this line in parametric form. If we desired the equation in one of the other forms, we've covered in previous videos how we could go about that. We'll see similar examples to this in your homework. Good luck.